I'm going to walk you through a one sample z-test using probably the easier method. The book gives you about 8 different steps. We are going to do it in about 4 steps here. And the 4-step problem is how I want you to do all your inferential testing. So today we're doing the one sample z-test. So your first step is going to be state, and this is a statement of the problem. So what are you trying to find? Are you trying to find that your mean is greater than the population mean? Are you trying to figure out comparing it to a certain number and so on? Our plan step is going to be your hypothesis. So you're going to demonstrate what you're trying to find. And I write my hypothesis a little bit different as well compared to what the textbook writes. Your solve is going to be computing your z-score, which you will use your formula z equals sample mean minus population mean divided by your standard error. So standard error of the mean. Once you do that, your conclude is going to be based on your p-value, which is your significance level. So let's walk through this, and I am going to just do a new slide here. And our statement in this question. So I am going to use the problem that the book uses as an example, but I wanted to use it as my example. So they talk about a professor that is looking at whether the class average falls within the boundaries of the average score for the larger group of students. He's kept good records, and he knows the mean and standard deviations of both his sample group and his population. So I'm just going to real quickly draw this out. If you look on page 193 of your textbook, you will find it as well, just so you have that information. So we're going to look at the size, the mean, and the standard deviation of both these groups. So he took a smaller sample group. Well, obviously I don't know how to draw a table here. So sample and population, there we go, that looks a little better. So the sample size, he had a class of 36 students. Total, he's had 1,000 students. The mean of the sample was 100. The mean of the population was 99. He had 5 standard deviations and 2.5. So that's the data I am looking at. So what they are trying to determine is he wants to know if his class average differs from the entire group's average. So the class average differs, meaning it's a two-tailed test. We're not trying to figure out greater than or less than, we're just trying to determine if it differs from the larger group average. And the reason we do this step is so that you can determine what you're actually trying to find. So the state step lets you look at it and determine, okay, I think that there is a difference, or I think one group is bigger than the other, or so forth. So your state step lets you make a comparison of the larger group. It helps you look at what you're trying to find. After the state step, you're going to plan, and your plan is your null and alternative hypothesis. Reminder, the null is h sub 0, your alternative is h sub a. So we're trying to determine that our sample group is going to differ from our population. So we want to determine that our mean is equal to 99 because that's our population, but we believe that it differs, meaning that we do not think that our sample group represents our population. And the way I was taught and the way I'm going to teach you guys is to just always use mu and compare it to a specific number, which I know is slightly different from the textbook. And if you want to do it the way the textbook does it, they look at it as how does the sample mean compare to the population mean. And we think there is a difference. So these both represent the same hypotheses. I would recommend doing it this way, but if you would like to follow along with the book, that is fine as well. And basically, if you remember, our null hypothesis is stating that there is no difference, meaning that our sample mean and our population mean are exactly the same. Our alternative hypothesis is saying that there is a difference. So we're trying to test against our null hypothesis and prove that it is incorrect and try to determine that there is a difference. We may or may not find that difference, but that is our goal. So our solve step is to use our formula to test that alternative hypothesis. And if you remember, we have mean minus mean, so sample mean minus population mean divided by the standard error of the mean, which is standard deviation divided by square root of n. So our sample mean in this group is 100. Our population mean was 99. Our standard deviation is 5. Oh, excuse me, it's 2.5. Okay, I've got the wrong one here. And our sample size is 36. So if you do the 2.5 divided by square root of 36 for square root of 36, you will get 4.42. So you'd have 100 minus 99 divided by 4.2, or 0.42, excuse me, which is 1 over 0.42, which gives you a z-score of 2.38. So the z-score of 2.38, we can go ahead and look up in table B1. So if you go to the back of the book to table B1, you are going to get a z-score of 2.38, and they're going to give you the area between the mean and z-score. And that area, let's see, 2.38 is 49.13. And I want to demonstrate this a little bit as to what that represents. And I'm a picture person, so I'm going to demonstrate that. So if we draw a normal curve here, we put our mean in. We are doing a two-tailed test, so not only do we have to go to 2.38, we have to look at negative 2.38. Remember, our normal curve is symmetric. So we know that the area between the mean and our 2.38 is 49.13. Okay, this other side is also 49.13 because it represents that entire middle area. So if I add those two together, I get an area of 98.26. Okay, I want to determine my p-value, which is what is left over in my tails, because I am doing a two-tailed test. So to figure that out, I need to go ahead and subtract my 98.26 from 1. So if I take 1 minus 98.26, I am left with, 100 minus 98.26. I am left with 1.74. That is what's remaining out in my tails here. This 1.74 represents the percentage left in our two tails. And since we are running a two-tailed test, we need to look at both tails combined. So we've got 1.74% of our data lies in those two tails. That number is less than our 5%, or our 0.05, which shows us that, remember this is 1.74% of our data. Since it is less than 5%, we can reject our null and accept our alternative that there is a difference between the sample score and the population score. So we always want to compare our values to that 5% or 0.05. That represents our alpha or significance value. If we're less than alpha, that tells us we can reject our null and accept our alternative. If our value is greater than our alpha or our 5%, then we fail to reject our null. So let me go to our solve step. For this one, or, oh, not solve, doing too many things here. Our conclude step, which is our final step, we will, since P is less than 0.05, so our p-value is significant, we can reject our null and accept the alternative hypothesis that the sample differs from the population. Okay, that would be the end of our problem. A little guide or a note. If our P is greater than 0.05, which is or 5%, we would fail to reject null and can draw no conclusions. If its P is less than 0.05, which is our 5%, reject null and accept alternative. Remember, when you are running a z-test, you are not actually testing the null hypothesis. You are trying to test against it. So you want to prove that the alternative hypothesis is correct. So you either accept your alternative or you will fail to, or you will not accept the alternative. You will never ever accept the null hypothesis.